All right, so here's another example. This comes out of Munson's book. A light aircraft with a wing area of 200 square feet and a weight of 2,000 pounds has a lift coefficient of 0.4 and a drag coefficient of 0.05. Determine the power required to maintain level flight. Okay, so we don't need to, but I like to draw like sort of a representation of what's going on right here, just to keep our sanity if we can. Here, so something like that. I didn't do a great job of that, but here is our weight, and here is our lift, and here let's call this the drag, and then there's going to be some type of thrust, maybe T, coming in there, right? And we're going to assume this is all in equilibrium. So the first thing to do as part of this is to figure out what the velocity has to be for this thing to be flying at constant flight, to maintain level of flight. So let's start out with what the lift has to be, right? And so the lift has to equal the weight, right? Because the sum of the forces in the y direction equals 0 if this thing's going to have level of flight, and therefore we're going to have a negative W and a positive lift. That's going to equal 0. So the lift is going to be equal to CL times 1/2 rho V squared A. It's going to be the wing area that we're going to use. So we can write out the velocity. It's going to be the square root of 2 times the lift divided by rho A and then the lift coefficient. So let's take that and go 2 times the 2,000 pounds, because that's the lift equals the weight, divided by the air, and we don't know the altitude, so we're going to go ahead and assume density is going to be 2.38 E minus 3 slugs per cubic foot. Now, airplanes fly up high and the air gets thinner as you go up higher, so for most cases we might tell you what an altitude is, but because we weren't told the altitude, we'll go ahead and use the standard atmosphere at ground level. The area is 200 square feet, and then the lift coefficient is 0.4. So the velocity to be able to do this is 144.9 feet per second, which, by the way, if you were interested, is 98.8 miles per hour. A good thing to kind of like think your way through. So that's what they need for level flight. So we want to figure out how much power is required to do that. And we know that the power is going to be equal to the drag times the velocity, right? So because this is force times the distance rate, right? And so that's what the power that's required out of whatever engines, or whether they be propellers or jets or whatever that are creating thrust, that thrust has to equal the drag when you're at a constant speed. So we need to find this drag, and that's found from taking the drag coefficient, multiplying by 1/2 rho V squared A. Now here is my thing. I've been trying to look through some of the books, the fluid mechanics books in this section, and I haven't seen one where it explicitly says that sometimes the drag coefficient is based on the wing area, because it should be the frontal area, I would think, but I guess in some circumstances they use that same area for both things, because they like to look at a lift to drag ratio or drag to lift ratio for some calculations. And if that's true, they must be using the same area for both things. But truth be told, that's not a very good approach, I think, for doing drag, is to use the area that's in the opposite, the perpendicular to the force, right? That doesn't make sense to me, but I guess maybe because wings have an angle of attack type of thing, it just makes more sense to use the same area for both the lift and the drag. That's what I've decided must be the rationale. So we stick the drag coefficient in there, and the density here, 2.38. And once again, I really think we should use a thinner density, but I already had it written out this way, so I kept it with it. So we use 144.9 that we found from the lift. That makes sure we square that. And then the area is 200. So I get that the drag on this is going to be 250 pounds, which doesn't seem like a lot. But now we can find what the power is going to be by taking 250, multiplying it by the 144.9, and you get pound feet per second. And so we usually want to use the 550 conversion, which is a foot pound per second per horsepower, and that'll give us the horsepower, and that comes out to 65.9 horsepower. Boom, boom. Okay, another short video, but a good problem, I think.